In this video, I'll be teaching you guys how to solve disks and washers. I'm going to show you a general formula that you can follow. And also, I'm going to visualize. I'm actually going to visualize using Desmos how you can actually, what's actually happening. What are you doing with your math, right? Because, okay, when I was learning this, my teacher did not show me Desmos representation when it would be just so easy to pull up some YouTube video or some Google search, some Desmos thing. But right here is a disk and washer that I'm about to show you. So we have a function, parabola. We're finding the area under the curve. This is a basic integral. The area under the curve is represented by a bunch of infinitely thin lines. And basically, you sum up all the areas of the lines until you get an integral, correct? Well, what would happen if we found the integral for this function? And let's move this into 3D now. What would happen if you found the integral for this function, right? And rotated it around the x-axis. So this axis, this arrow right here represents what we're rotating around. And what happens if you were to rotate it around the x-axis? Well, it would look like this. Now the integral, that's still the same for if you just calculate for the function itself. But how do you calculate the volume of this rotated disk? Well, it's actually quite simple. Since an integral is comprised of a bunch of lines, each line represents a radius of some circle. So let's go ahead and rotate this around once again. And if I were to try to show you what it looks like on this end right here, you know, kind of flatten it out a little bit. Okay, maybe I could. Okay, well, you get the point. There's a circle at the end of this, right? You have a circle here. And how do you calculate the area of a circle? Well, you can calculate the area of a circle by multiplying radius times 2 pi. Well, radius squared times pi, correct? So radius squared times pi is the area for a circle. Now keep in mind, an integral has infinitely many Riemann sums, or infinitely super thin lines, technically, Riemann sums that are super thin, basically. And if you multiply each of these lines by pi, and then you square each of these lines for this Riemann sum, and you add all of those areas that you actually got together, well, don't you have the volume of the revolution? So this is basically the core concept of what a disk washer is, and I'll show you the math for that actually and what I mean by that. But keep this visual in mind. Now, this is an example of a disk. Okay? It's not really a washer because a washer is hollow on the inside. So currently this integral is not hollow. But basically the fundamental concept of a washer is still the same, and I'll show you what I mean by this. So this right here is an example of a washer. Now, the fundamental concept of a washer is still the same, but instead you use two functions. So one of the functions gives you the radius of the larger circle, and that is the upper bound of your function, in this case this top curve here. And the second function you use is the radius of the smaller circle. But this smaller circle takes into account the hollow area, the hollow volume of your rotation. So let's go ahead and rotate this. If I were to rotate this to make it visually easier for you guys to see, right here is a hollow portion of the circle, of the volume, sorry. So the inner portion of this is hollow, and this is kind of the shape it makes, as you can tell by all these lines that Desmos was so nice to make. And I'll leave a link for all these examples in the description. You can play around them as well if you want. But right here, let's go ahead and explain how the math works, and I'll show you all the formulas and everything. But basically, instead of calculating a bunch of radiuses and finding the areas, right, what I said before, you can find the radius of all of the points along this curve. So you can find the y values of all the points along this curve, and all the y values will represent all the radiuses of the circles rotating around. And again, you want to square the radiuses and then multiply them by pi. So if you find, let's pick any point here, doesn't matter. If you pick some point here, like let's choose over my cursor, and you keep that x value, right? So this is, let's say, an x equals 1. This is position x equals 1 right over here. Right? And this y value had some radius. You'd be able to calculate the area of the circle as you rotated it around the x-axis by using the y value at this function. The y value at the function is the radius. So if you square the y value and then multiply it by pi, you get the area of the circle. But you won't get the area of the hollow portion of the circle, sort of like the donut cross section that this makes. So if I were to rotate this around and I wanted to take a cross section out in the middle of right here along my cursor, you would get some donut shape for the function. So how do you take into account the inner hollow portion? Well, technically this lower bound function has a function as well, right? And you can take the y value of that function at x equals 1, per the example that we showed, and then you can subtract the area of the circle that you calculated using the y value of the lower bound function. So when you subtract the larger area from the smaller area, you get the area of the donut that actually forms. Now, if this is confusing to you, of course, the math will help a lot. But visualization, I would say, matters the most in calculus. So let's go ahead and do the math. Now, specifically what you see here is the general formula for a washer. Now, for a disk, all you have to do is omit this part of your function. But what we basically have is the function of the upper bound squared minus the function of the lower bound squared times pi. And of course, if you distributed the pi into everything, you would technically have, so if I distributed the pi into this, you would have the function of the upper bound squared minus blah, 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 right? Minus this part. But if you put pi here, pi times your function value squared is analogous to pi times the radius squared, right? Your function value is the y value, and the y value of your function is the radius of the circle that you're rotating around. But this function that you're seeing is specifically for only if you're rotating the function around the x-axis. Okay? This is specifically for the x-axis. I'll have a separate video for functions that rotate around the y-axis, or disks and washers around maybe some vertical line that's up here. So maybe if you had some function that looked like this, right? And, you know, cut off from here to here, maybe instead of rotating it around the x-axis, you know, it kind of spins around like this, you rotate it around up here. So that means it will rotate up like that. Right? This is the line y equals 5. So this is just the formula for a function that rotates around the x-axis. Keep that in mind, the formula that you're seeing on the board. But let's go ahead and do some problems using this, and I'm going to erase it so that you guys can keep the logic in mind more like than anything. So for this problem, we want to find the volume of the revolution about the x-axis for the function square root of x from 0 to 4. So our general formula, actually you guys do this first. Do it first. Try it out using the general formula. But basically what we have is just a washer. Since there's no lower bound, sorry, a disk. Since there's no lower bound for this, we just don't have any hollow spaces inside of your function. So we only have the upper bound portion of our general function. Therefore, our function, our integral, looks like this. 0 to 4 are the bounds given for our function square root of x squared. So the function squared, right, dx. So this is analogous to saying radius squared times pi. This is the area of your circle. And when you take the integral of some area, you'll get some volume. All right, let's go ahead and evaluate this. This basically is just pi times the integral from 0 to 4, square root of x squared as well, just x, right? So if we evaluate this integral, we have pi times x squared over x from 0 to 4. So if we plug in 4 here, we get 16 over 8. So this is 8. Let's make some space down here. This is pi times 8 minus 0 over 2, which is just 0. So the answer is 8 pi. So let's use the washer method for this. First, we need to find the function that is the upper bound. This is not directly stated in the problem, so we want to find the upper bound function. If we draw out our two functions, we have x squared, looks something like this, and x equals y looks something like the green arrow. Let's go ahead and underline this with green, underline this with red. So now we can tell which ones are the upper bounds. The upper bound is given by the function y equals x, right? This bounds the upper portion of this region here. And this is the region that we want to rotate about the x-axis. So we're kind of rotating this around, if you can imagine it. Actually, I can keep the arrow, if you can imagine that. So how do we set this up? Well, general formula. Remember that? So pi times the bounds of the integral. The bounds are 0 and 1. And 0 and 1 are also the intersection points given here by the two functions. So this right here is x equals 0, and this right here is also x equals 1. So our bounds are 0 and 1 for the function. And remember, upper bound, so the function of the upper bound, which is x squared, minus the function of the lower bound, x squared squared dx. All right, let's go ahead and evaluate this integral. So this integral basically equals x squared minus x to the power of 4 dx. Let's go ahead and evaluate the antiderivative. So we have pi, and the antiderivative of this is x to the power 3 minus x to the power 5 over 5 from 0 to 1. So let's go ahead, pi times 1 over 3 minus 1 over 5. And the 0 doesn't do anything, so we can just omit that. We don't have to plug in the 0 for the fundamental theorem of calculus. All right, now once we evaluate this, well, if you want me to simplify it, it's 2 over 15 times pi. So this right here is the volume of this area revolved around the x-axis. All right, let's do one more washer problem. I think you guys get it by now. And if you need a little more work on discs and washers, I'll have more videos that show you how to rotate a disc about the y-axis, and also how to rotate a disc about some line of choosing. So you don't have to always rotate it about the x-axis, you can rotate it about the y-axis. There's an even more general formula for that. But go ahead and start this problem. Oh, by the way, link will be down in the description for those videos, for your convenience, of course. But let's go ahead and solve this. Last one, let's draw the functions to find the upper bounds. And listen, I can already tell that the upper bound is y equals 1, because this is what both the functions look like, right? So the upper function is y equals 1. Let's go ahead and set up with the integral. Pi from 0 to 1 for the upper function. The upper function is simply 1, so you have to square both of them. So upper function squared minus lower function squared. So the lower function is x squared in this case. Lower boundary function. So what we have here is simple integral. Let's go ahead and simplify this a little bit, which is just 1 squared. It's just 1 minus x squared squared is x to the power of 4 dx. So if I were to find the antiderivative of this function, antiderivative of 1 is just x, antiderivative of x to the power of 4 is x to the power of 5 over 5. And the bounds are 0 and 1. So let's go ahead and evaluate this. We plug in for 1, so we get pi times 1 minus 1/5. And then 0 does nothing, so this is basically our answer. You can leave it in this form, but if you want to simplify it, it will just look like 4 over 5 times pi. So really, if you can memorize the general formula that I showed earlier on in this video, you're good to go with most discs and washers. Now, the problem once you'd rotate about the y-axis, it's going to be a little different, but the general formula still holds. That's really all. So if you have any questions, put it in the comment section. And if you found this video helpful, consider subscribing and liking the video. Also, thanks for 200 subscribers. I just hit that like 10 minutes ago. I was watching my subscriber count while playing Grow Garden on Roblox. So I appreciate the support, guys. Every one of you are amazing. And thanks for watching.